Welcome to this GERAD webinar. Today we have the pleasure to welcome Professor Franklin Djeumou Fomeni from Université du Québec à Montréal for a presentation entitled Recent Algorithmic Advances for the Quadratic Knapsack Problem. But before his presentation, I would let Franklin introduce himself and present as well his research interests. So please, Franklin, go ahead.
Okay, so I should share my screen first. And okay, just to make sure that everyone can see my screen.
Yeah, it's okay. Go ahead.
Yes.
Okay, thank you. So thank you for Professor Ban for giving me this opportunity to talk about my research. So first, before I go into the details of my research, I will talk a little bit about myself. I was born and raised in Cameroon, where I grew up and obtained my bachelor degree there in Cameroon in mathematical sciences. I also obtained a master's degree in mathematics. Then after that, I moved to South Africa at the African Institute for Mathematical Sciences, AIMS. So some of you may have heard about AIMS with the recent partnership between AIMS and IVADO. So I went there and did my postgraduate diploma. And after that, I did a second master's degree at the University of the Witwatersrand in Johannesburg, still in South Africa. Then after my master's degree, I moved to the United Kingdom, where I did my PhD in operations research with Professor Adam Letchford. And I was interested in the quadratic knapsack problem, which I will be talking a lot about this morning. Then in terms of, I had a couple of postdoctoral experiences, which started here in Montreal and at GERAD with Professor Miguel Anjos. So I was here from 2014 to 2016. And we were interested in equilibrium in energy markets. Then after that, I went back to Lancaster to work on a problem in air traffic flow management. Then I came back to Montreal and had my third postdoctoral spell at UQAM, where I was working on developing intelligent logistic systems with Professor Theodore Kreinig and Walter Ray. And since autumn 2020, I've been appointed as an assistant professor at UQAM. So recently, I applied for a research NSERC discovery grant, which I obtained. And because of the research program that I will be developing throughout this, the tenure of this grant, I think that it fits well with the interest of GERAD, which is why I want to become a member at GERAD. So going now into my presentation itself, the research presentation. Okay, so I will be talking today about some recent algorithmic advances for the quadratic knapsack problem. So what is the quadratic knapsack problem? I will start by introducing what the quadratic knapsack problem is, and I will talk about some algorithms that exist for solving this problem. Of course, because it's a difficult combinatorial optimization problem to solve. Most of the successful algorithms use like the branch and bound framework. So if you want to do a branch and bound framework to solve this kind of problem, you need a heuristic algorithm. You need to solve the continuous relaxation, which once you solve, you can use cutting planes to have good quality of your relaxations, and then you can throw everything into a branch and bound framework or a cut and branch. So our approach, my solution approach for the quadratic knapsack problem follows the same kind of steps to develop the algorithm. But in this presentation, I will talk about the specific details of what makes our contribution in this area particular and specific. So first of all, most of you know about the linear knapsack problem, maybe from your undergraduate degrees in or introductory course in optimization. The linear knapsack problem, we have a set of items. Each item here comes with a profit value and then a weight that goes with it. And on the other side, you have a knapsack that has a limited capacity. And the idea is to select a subset of the items that can fit inside your knapsack with the aim of maximizing the profit, because each item comes with a profit value. So now, let's assume that we have, again, a set of items. We also have a knapsack with a limited capacity. Each item comes with a weight and a profit value. And then for every pair of items that you select, there's an additional profit. So you can think about this as if you are, for example, planning to locate charging stations for electric vehicles. That's one example. By building charging stations in Montreal, for example, that will, the idea here is to try to get as many people as possible to buy electric vehicles and not having a lot of worries about the availability of charging stations. So if you build a charging station in around Montreal, that would be good for the people living locally in Montreal that do not need to make long distance travels. But if you also build charging stations in, let's say, Trois-Rivières, you will also have the same dynamics. But if you build both in Montreal and in Trois-Rivières, you will be able to maybe get some of the people that do long distance traveling between those two cities to purchase electric vehicles, because usually when someone wants to buy an electric vehicle, the first idea is, what's the range? Will I be able to make long distance traveling with my vehicle? So that's how the quadratic profit comes into action here. And if you think of many other location problems, this kind of quadratic dynamic comes into play, because by selecting a pair of items for every pair of items that you select, there is a local profit everywhere, but there is also a correlated profit that comes into play, which is why what the quadratic knapsack problem attempts to model. So mathematically speaking, we have a quadratic objective function. Here the quadratic terms is the product of two variables, which represents the fact that you are selecting pairs of variables. In terms of constraints, we only have a single linear constraint, which may look very simple, but the problem is actually very complicated, because if you take the continuous relaxation of this problem, it will be very poor, okay? So it's very challenging. So in terms of application, why is this problem important? I gave you an example with the location of charging stations for electric vehicles. You also have applications in terms of airports, freight terminals. Also, if you go into finance, you can think of, if you want to model the portfolio selection and take into account the correlation between the different portfolios that you may select, you can model this problem as a quadratic knapsack problem. So although at GERAD, many people work on vehicle routing problems, and for some of you already may know that when you solve some variants of the VRP, the quadratic knapsack problem may appear sometimes in your branch and price algorithm as a subproblem, and you need to solve this subproblem very quickly. So that needs some sophisticated algorithm from the quadratic knapsack problem. So those are some of the applications of this problem, which is why it is interesting and important to study this problem here. So in terms of challenge, we know that the linear knapsack problem in the literature, it's said to be NP hard. But in 1957, there was an algorithm, dynamic programming algorithm, which could solve this NP hard problem to optimality using a pseudo linear time. But when it comes to the quadratic knapsack problem, the NP hardness here is in the strongest sense possible. That was shown in 1998 by Caprara and co-authors. So when I started working on the quadratic knapsack problem when I started my PhD in 2011, there were few algorithms that existed already for solving the quadratic knapsack problem. And one of the most powerful one is by Caprara and co-authors. The algorithm is based on Lagrangian relaxation and some greedy heuristic to find feasible solutions. But this algorithm, although it's very powerful, it can only solve problems with up to 400 items. And 400 items here concerns the cases where your profit matrix is fully dense. If your profit matrix is sparse, then you may be lucky if you are able to solve instances with more than 150 items. So that some drawback with this algorithm, even though it's very powerful, very fast, but it has this limitation. There's a different algorithm by Billionaire and Soutif, which does the inverse. So it's very powerful for sparse instances, but for dense instances, it is very poor. But it is limited to 300 items, which means that in practice, if you have a quadratic knapsack problem with more than 400 items, it's impossible that you can solve it using, you could solve it using the existing algorithm. So that the challenge I set myself to address. What is my solution? The solution approach used in this for this problem? Like I said, the main framework is the branch and bound idea. So branch and bound, you first need to a heuristic solution that will give you a good lower bound, a good feasible solution. And you also need to solve the continuous relaxation that will give you an upper bound. And you combine this into your branch and bound algorithm. And if you are lucky enough, you can get to a solution. But after investigating what was already in the literature, I realized that the gap, the difference between the existing lower bound and the upper bound, it's usually very large. So definitely that will be a drawback for the algorithm when attempting to solve larger instances, because it will run forever and ever trying to reduce this gap. So I set myself the idea that what if before going into the branch and bound, we try to improve the different bounds, both the lower bound and the upper bound, so that we get something which are very close together, and then we will only spend very few time into the branch and bound process. So we try to develop some algorithm that will give us lower bound. We use the idea of cutting planes, which I will go into the details very soon, to find upper bounds. And we also have some primary heuristic that intend to improve the quality of the lower bound obtained. And finally, we throw everything to the branch and bound algorithm. So what are the details of our heuristic algorithms? I will talk about two heuristic algorithms in particular. The first one was developed in 2014 during my PhD, which is based on dynamic programming. So the idea comes from the fact that we know that dynamic programming works, can find the optimal solution for the linear knapsack problem. Now, what if we try to use this idea and apply it to the quadratic knapsack problem? Will it still work? One problem is that you cannot, the Bellman principle of optimality, for those of you that are familiar with dynamic programming, does not hold in this case. So that is impossible. And the fact is that you cannot guarantee that the this state function as defined here, it's exactly the maximum profit that you can obtain with a subset of the first k functions, first k items. Okay, so what we did is that we first redefined the meaning of this state function. So instead of defining it as the maximum obtainable profit, we define it as the best packing found by, because now it becomes a heuristic algorithm. So we will call it this best packing found by the heuristic that uses a selection of the first k item and total weight is equal to R. Now, if you want to define this as the best packing for the first k items, you need to keep track of the set that is able to give you this packing. So that's why we define the set SKR here. What is the impact of that? Using these two terms, we can define a dynamic programming algorithm as normally. So what you can see here is that we have a first for loop which operates over the items, and a second for loop which operates on the capacity that is used, on the resources that is used. So this algorithm we have, in terms of complexity, we have an order of n with the first for loop, an order of c with the second for loop. And when we come down to computing the profit of the packing of that, the best packing, it contributes to an order of n. So in the end, we have an order of n squared times c, which is the complexity of the algorithm. So it becomes pseudo polynomial, pseudo quadratic or pseudo polynomial if you want. But the major drawback here is that the set SKR, it's being stored for every k and for every r value. So, and for every k and r value, you need a vector of n entries to store this. So which gives you a memory requirement in the order of n squared times c. What does that mean? It means that if you want to solve instances with about 500 items, your everyday laptop will not be able to, will run out of space, because it's a lot of memory space required for this algorithm as it stands. But what we realize is that for the second for loop in this algorithm, if we invert the direction of the iteration, so instead of going from 0 to c, we now go downwards from c to 0. That can allow us to drop the k component in both the state function and the set SKR. So that brings us down to an algorithm that will only use an order of n times c in terms of memory space, but the complexity stays n squared times c. So we added some ingredients to improve the quality of the results that are obtained. For example, we decided to define some orderings of the items at the beginning of the algorithm. Then we add some tie-breaking rule and local search at the end of it. So what do we get as a result of this algorithm? We try to compare it, the new algorithm, with the existing heuristic that are found in the literature. The CHM is by Chailloux Hansen. This is Pierre Hansen from HEC Montreal, and Billionaire and Calms. So those were the best two deterministic heuristic so far for the quadratic knapsack problem. And those are represented by the red and yellow lines. So our new dynamic programming is represented by the blue line. You can see that the optimality gap for our algorithm is nearly flat. And if you look at the computational time, it's still the same kind of pattern. It's the computational time required is very low compared to those two existing algorithms. So we kind of have a double jackpot where you win in terms of quality of your solution and also in terms of the computational times. That is very good for this problem. But after we published the paper in 2014, there was a guy from Denmark, from Copenhagen. He was curious about the fact that the quadratic knapsack problem is said to be NP-hard in the strong sense, but an algorithm can perform this well on the problem. So that's a bit contradictory. So he decided to study the asymptotic nature of the quadratic knapsack problem. And these tests here are based on some instances that were used in the literature since the creation of the quadratic knapsack problem. So what he realized is that the way those instances are generated are not challenging enough to represent the NP hardness property of the quadratic knapsack problem. So what he did, he came up with some instances that could challenge all the existing algorithm and show that these are the instances that should be used as benchmark instances for the quadratic knapsack problem. But unfortunately, our paper was already published at the time, so we could not reassess things later on. But what I've recently done is that I said to myself, we have this algorithm which was doing well, then these instances came along. Can we modify the algorithm in such a way that it can also perform well on those challenging instances? The idea brought me to the fact that the initial dynamic programming is implemented using the items one after another. So it doesn't take into account the fact that there is a profit related to the selection of pairs of items. So that is an information which is not being captured in the existing dynamic programming algorithm. So I said to myself, how could I take the dynamic programming approach and move it up to the space of the quadratic variables so that I could capture this quadratic profit, additional profit that is brought in by the selection of pairs of items. So how is that done? We just need to reformulate the problem. We separate first the linear profit part of the objective function, and then we have the quadratic contribution of the profit. Then the xi times xj variables, we replace it with a new variable which will be called yij. So it makes our objective function linear, but the quadratic nature of the problem is brought into the constraint set. When you do this, it makes your problem, it doesn't make your problem less hard, but I mean, the problem becomes even more complicated because now the nonlinear is in the objective function. But for this heuristic, we are not addressing that at the moment. We are just going to implement the dynamic programming, but in the space of lifted variable, which means that we will consider both the items individually, and then we will also consider the edges in the graph represented by the problem that we have, which means by considering pairs of items in our dynamic programming. So that's an algorithm that I developed recently. And of course, when you do that, you need to address some minor issues, such as if you are considering an edge made up by two nodes that represent pairs of a pair of items, you need to be able to calculate in an appropriate way the contribution in the weight, because that will be using a resource in your dynamic programming process. And you also need to find a way to calculate appropriately the contribution into the to the profit function value at the end. So how can that be done? If you take an edge represented by a pair of items, of course, if both items are not yet included into your knapsack, then the weight contribution is the sum of the two. But if one item is already in your knapsack and the other one is not, so the weight is only the weight of the new item, because that's the additional weight that you get. But if both are already into your knapsack, then there is no weight contribution. When you go to the profit, is basically the same kind of process. You take the profit contribution, the individual profit contribution of each items, the profit contribution of this pair of items, and the contribution to the profit of the pair of for each items that you are adding in your edge with the items that are already into your knapsack. So that's how you do this when you lift your dynamic programming to the quadratic space. So that gives us an algorithm that now runs in terms of n squared times n cubed times c. So the addition into time complexity here is a factor of n, but we also modify the memory so that the memory requirement will stay at n times c. And we have a local search procedure that is implemented at the end, but this local search procedure too is implemented in the space of lifted variables. So now we made some tests. The test with, of course, we did some tests with the old ways of generating instances, and we obviously have zero optimality gap everywhere. But in this table here, we are only showing results for the hard, challenging instances that were published in 2016 and that were developed by Schauer from Copenhagen. So these are those instances here. We can see that the red line is the optimality gap that were obtained with the previous dynamic programming algorithm. But with the new dynamic programming algorithm, we have a nearly zero gap for all those instances. This is about 800 instances for which we have nearly a zero gap. So this is a major, major step forward for addressing these challenging instances. So that's it for the heuristic part of the algorithm. Now I will move into the cutting plane phase. So when you want to solve if you want to use cutting planes for the quadratic knapsack problem, of course, the first thing is to find a linear relaxation for which you will be able to use tools that exist, such as the LP solver of Cplex. And if you, so first you need to linearize your problem. Of course, it is done. I presented a first part of it where the quadratic term was taken from the objective function to the set of variables, to the set of constraints. Now you can replace that quadratic term from the constraints with linear inequalities. These inequalities are known as the Markovic inequalities. So you use them and your problem becomes linear. But still, if you solve the continuous relaxation of this problem, the bounds that you will obtain are very poor. So how do you improve the quality of the upper bound obtained this way? We are going to use cutting planes to do that. And from in our research, we investigated some families of cutting planes, and we found that there are some of the cutting planes that were very more promising. So one very promising one was the RLT cutting planes obtained from the RLT techniques, linearization and reformulation and linearization technique. That's from Adams and Shirali. We also have the triangle inequalities from Padberg. And we also have covert inequalities. Covert inequalities, it comes from the merge of two different kinds of inequalities. So for the linear knapsack problem, we know of the cover inequalities that are very good. And for people familiar with network optimization, you know of the tree inequalities that are also very good. So now the idea that we use here is that what will happen if you build tree inequalities that are where your tree is based on a cover set from the knapsack problem. So that allows you to bring in the knapsack nature of your problem into the tree inequalities. So that will definitely give something more interesting than just applying the tree inequality blindly. And the same thing happens if we use, again, from the knapsack problem, we know of the lifted cover inequalities. What if we apply the RLT techniques to the lifted cover inequalities? That will also definitely bring in the knapsack structure of your problem in the type of inequalities that you generate. And finally, the last families of inequalities, the double star inequalities that was developed by us in 2016. It comes from studying the polyhedral structure of the quadratic knapsack problem. So those inequalities come from there. In terms of, in details, the RLT first level, you take your knapsack inequality and you multiply both sides by one variable. So if you multiply that, on the left-hand side, you have a quadratic term. On the right-hand side, you have a linear term. But your quadratic term, you already have Yij variables to represent those quadratic terms. So you simply replace them and you obtain linear inequalities. So that's the idea of RLT first level. In terms of triangle inequalities, they are well known in the literature. They have this fixed form here, so I will not go into the details of that. In terms of lifted cover inequalities, and like I said, knapsack problem, you have the cover inequality. What's a cover set? It's simply that if you have a knapsack capacity of C, and you have a subset of your items whose total weight is larger than C, what you can see is that from this subset, you cannot take all the items because the capacity, the total weight is already larger than the capacity. So you can take at most the cardinality of the set minus 1. So that's the cover, and this defines the cover inequality. So you can take at most the cardinality of your cover minus 1. And the lifted cover is that you can also associate some of the items that are not part of your cover set. Now, our idea of inequality is that if you take this lifted cover inequality and apply the idea of RLT onto it, you will get what we call the lifted cover RLT inequalities. For the tree inequalities, also you start with a cover set and then build your tree, your tree from this cover set here. So I will not go into the details of that. Now our double star inequalities here, just briefly speaking, it comes from this graph structure. So you can think of it as trying to write the center of gravity of this graph structure in two different ways. There is one which is more stable than another representation if you focus on the two nodes that supports the double star graph. So that's the idea of the inequality. I'll be happy to discuss the whole idea with anybody later on. So now, when you talk about cutting planes, there is one question that comes into mind, because it's always very nice to have any kind of fancy cutting planes that you can throw into your problem. But one thing is, how useful are they? The usefulness of cutting planes is not only in terms of the quality of the bound that you obtain, but also in terms of how easy can you generate these cutting planes? Because if you can spend 2 days to generate a cutting plane that will reduce the gap by 1%, it's useless. So you need to solve what we call separation algorithms to generate your cutting planes. So in terms of separation algorithms, a separation algorithm is that you give it a solution from your continuous relaxation problem, and you give the structure of your family of cutting planes. The separation algorithm will generate some cutting planes in this family that are feasible, that are violated by the fractional solution that you've input, and you can then use it. So when it comes to the RLT inequality, you can just enumerate all of them. They are a total of 2n. So that's very easy to separate. Triangle inequalities also, if you want to enumerate all of them, you have a total of n cubed. So you can do enumeration for all of them. But we have currently developed a heuristic way of generating the strongest triangle inequalities that runs in linear time. So you don't have to do the n cubed times to generate triangle inequalities, regardless of the problem that you're solving. It's not only for the quadratic knapsack problem, but it's for general quadratic problems with binary variables. For the lifted cover inequalities, we also have a separation algorithm that runs in n squared times. Same for the double star inequalities. So I will leave the details for if you need some discussions later on. Now, we ran some experiments with our cutting planes. So in the first subgraph that we have here, we are considering the old ways of generating quadratic knapsack problem instances. So I should mention that these cutting planes were developed before 2016 when the hard QKP instances was published. So these results are based on those. When the profit matrix is very sparse, what you can see here is that combining all the 4 families of cutting planes that I've presented will give you the best bound, okay, the best upper bound. But when your profit matrix is dense, fully dense, you can see here that the best one is the purple line, which represents the RLT combined with the lifted cover inequalities. That can sound weird, that when you throw in all your inequalities, you get worse bound than when you only use RLT and lifted cover inequalities. So, but indeed, it raises an interesting point for future research here, is that the order in which you bring in your cutting planes is important to the quality of the bound that you will get. So that's a way of, this sequencing needs to be studied. And also we need to study the structure of the problem against the kind of cutting planes that can be used. Which of these cutting planes is more useful for which type of problem? So that is part of some of the things that will be studied in the future, because that's a very important point here. Now, if you want to look at the double star inequalities that we developed, because our double star inequalities is in fact a hierarchy families of inequality, which the idea is to strengthen the hierarchy family of RLT inequalities. So it means that whatever level of RLT inequalities you generate, we can find stronger inequalities using information from the higher level of your hierarchy of your RLT that are stronger than the level at which you are working. So for example, in this case, the linearization of our quadratic knapsack problem is in the space of RLT level 1. So we use the double star inequalities, which is kind of approximating the inequalities from the space of RLT level 2, but using variables of the space of RLT level 1. So what do we get here? You can see that with a complexity of n squared, our double star inequalities, the gap is nearly equal to the gap of the RLT second level. So that's what you get here, because our gap is represented by the blue line, and this RLT second level is the yellow line. So you can see you get almost the same you get almost an exact approximation of the second level RLT using variables in the space of first level RLT. So that's it for the cutting planes. Now I will move into our branch and bound framework. I will say branch and bound, because now we have a heuristic algorithm that is able to generate feasible solutions. We have cutting plane phase that is able to find a stronger upper bound. So what we do now is we want to throw it into a branch and bound solver, okay? But before we do this, we try to do some tricks at the beginning in terms of trying to reduce the number of variables. So can we try to eliminate some of the variables in the problem so that the size of the final problem that we throw into Cplex, it's the smallest size as possible. So that constitutes the variable reduction procedure of our algorithm. So how does it work? Is that if we consider them in our linearization of the QKP, we take the three McCormick inequalities that are used to replace the quadratic constraint Yij equals to xi times xj. So these are the three inequalities. We will define for each of them the dual price for each of the constraints, and we also define the reduced cost of each of the three variables, meaning xi, xj, and xy, or yij, sorry. So what we have here is some results that allows us to eliminate some variables and some constraints. So for example, the first one, if you take the reduced cost of, if you solve your continuous relaxation and you find that a specific variable Yij is equal to 0. Now, you by trying to switch this constraint, this variable on, meaning bring its value from 0 to 1, it means that because Yij cannot be 1 if xi and xj are not 1. So it means by bringing this up to 1, you will also be bringing xi and xj up to 1. That is reflected into the reduced cost of all these three variables. So the sum of the reduced cost of these variables will represent by how much your upper bound will be improved. Okay, improving means will decrease because we are maximizing our problem here. So now, if this improvement takes you below the lower bound that you've already obtained, it means you can remove the Yij variable. You can set it to 0. Okay, so that's the idea of the results that we have here. So we basically use some dual proper characteristics of the variables and the constraints to reduce some of them to get before we throw everything to Cplex. Now, what's, for example, the impact of doing this reduction procedure? You can see that by doing this, the different box plots that we have here represents the different density of your profit matrix. So for example, when you have 25%, it means that you have about 25% of non-zero entries in your profit matrix, 50% non-zero entries in your profit matrix, and so on. So we can see that when your profit matrix is sparse, the reduction process is not that, it's useful, but it's not that good, okay? Because we can reduce about 20% of the variables. But when you go to the dense cases, you can see that the reduction becomes very significant. You can reduce even up to 60% of your variables, which is very good. So if you go from a problem with 1,000 variables, you can end up with about 400 variables, which is good for Cplex to solve, okay? So now we have that, all the ingredients set up to use our branch and bound process. This was done using Cplex. There is a reason why we did not implement a full branch and cut, because we decided to limit the cutting planes at the root node. The reason for that is because we have many families of cutting planes. We've noticed some dynamics in terms of some of them are good for some problem types, and some of them are less interesting for some problem types. The order in which, the sequence in which we call up the cutting planes also have an impact in the overall result. So you don't want to throw something at the different nodes of your branch and bound without knowing exactly what that these cutting planes will be useful. Otherwise, it will contribute to making your overall branch and bound algorithm running time worse. So that's the reason why we did not go yet into a full branch and cut algorithm, but that's the next step. But before that, we need to study the impact of individual cutting planes that we have to specific problem types. Then we can use it into a branch and cut, knowing that they will be very useful. So when we did our overall cut and branch algorithm, on those instances, we try to compare our result with the best algorithm of Caprara and Pissinger and Todt, which was published in 1999. I'm confusing the date. So it's 1999 for the published version of the paper. So you can see that the first row here, the second column, CPT, is actually the running time of their algorithm. So I will start with the fully dense matrices. You can see that their algorithm is very fast compared to ours. It's like 10 times faster than ours. It can solve up to 400 instances. But when you reduce the density of your profit matrix, you can see that their algorithms start to struggle. But our algorithm is consistent all over. It can solve any type of quadratic knapsack problem, and within a limit of, I think here is about 2 hours to solve the problems, okay? Now, if you increase the size of your problem up to 850 items, then we are still able to solve them within 3 hours. And in this box plots here show the distribution of the running time. You can see that most of the time we can solve them within 2.5 hours for a larger instances. So this algorithm was published last year, and of course it remains that the difference between the quality of the gap lower bound doesn't use the new heuristic algorithm that is developed. So of course, by using this new heuristic algorithm and by studying the structure of the cutting planes with the problem and what way it can be useful, we can be able to come up with an even much stronger algorithm. So just to wrap up, in this presentation, I presented 2 dynamic programming based heuristic algorithms for the quadratic knapsack problem. I presented some families of cutting planes that are useful for the quadratic knapsack problem, but still needs to be studied further to see, to distinguish which one can be used for which type of problem with expectation of having some much interesting results. And our cut and branch algorithm can solve instances with up to 850 items. So there are some next steps to be done. Of course, consider the implementing a full cut and branch and cut framework. and use some learning to see the impact of the different cutting planes that we may have. And finally, of course, we can also still develop some new families of cutting planes by studying this polyhedral structure of the problem. When I was doing that during my PhD, there were a lot of promising cutting planes, so which need to which requires some more attention. So those are some ideas to be investigated next. So for that, I would like to thank you for your attention.